Hi everyone, I'm Sanjana and today I'll be taking a class on Induction and PHP. At any point, if you're not understanding or if you want to ask something, please feel free to speak. You can preferably speak instead of use chat. So let's start. So first of all, what is induction? So induction is a technique which is very commonly used in math olympiad problems, especially combinatorics and also number theory and algebra. So induction works like this. So what you want to do is, so the problem usually would ask you to prove something for all integers or natural numbers or something like that. So what you can do is, if proving manually for each and everything is kind of hard, then instead of that, an easier thing to do would be to prove it for a base case, which is usually like one or a small number or something like that. And then you prove that you assume it till n minus one. And then you prove that with this information that it's true for n minus till n minus one, you prove it for n. So assuming this is called the inductive hypothesis. And usually in some problems, it might not even be possible to prove for everything. So you have to use induction. And a nice way to look at this is to, instead of thinking of it as going from one and then proving for the next one. So you know that if it's true for n minus one, it's true for n. So it's like a domino effect. Like you can prove for one, and then that means it's true for true for two, and then for three, and so on. You can also think of it as reducing the case for n to the n minus one case. Because in many problems, that's a much more natural way of looking at it, like reducing it to something smaller. Especially when we come to strong induction,
Sanjana.
which we look at. Yes. Okay. So, especially when we come to strong induction, which we look at later, this reducing idea is much more natural. So just to see how induction works, we look at like a very simple example. So suppose you want to prove this like very basic thing that the sum of integers till n is n into n plus 1 by 2. So obviously one way to do it is by pairing 1 and n and 2 and n minus 1, which is called Gaussian pairing. But you can also do it by induction. So how you do it is, the base case you want to prove for 1, obviously, and that's obvious because 1 is equal to 1 into 2 by 2, obviously. So now you want to somehow show that proving for n, you can basically reduce it to the n minus 1 case. So this is what you want to prove, right? Now suppose you subtract n from both sides. Then what happens? Because you want to make it till n minus 1, right? So if you subtract n, then the LHS becomes the sum till n minus 1. So you get this. And here what you get is n plus 1 by 2 minus 2n. And notice that this is like the exact same thing, but for n minus 1. So here you've basically reduced n to n minus 1, which is what you wanted to do. Now the thing is you can keep on reducing, right? In the same way you can just take n minus 1 as your new n and reduce it further. You can go all the way to 1, which we've already proven. So this is how induction usually works. So now let's try a problem. This is IMO 2000 P4. And this is kind of a long problem, as in there are a lot of cases you need to check. So I won't be doing the full thing, and you can try to complete it as an exercise. But what I really want to show in this problem is how induction makes it much, much easier than just proving for everything. So you can try this for like 5-6 minutes. And if anyone has any ideas, please unmute or say it in chat or something. Also, if you've seen any problems before, or if you get it really fast, please say it in private chat. Otherwise, everyone will see it. So I'll give a small kind of hint. So basically what you have is you have three boxes and you have cards from 1 to 100. So instead of thinking of it as 100, let's just think of it as some n. And the magician is putting them into three boxes such that no box is empty. And now what happens is a person draws a card from two different boxes and he says their sum. And from the sum, you should be able to identify which pair of boxes the person got the cards from. So the thing is, like, if you just take all the pairwise sums of these two and of these two and of these two, the sums that you get must be unique. So if there's some sum here, it should not appear in this one or this one because you should be able to say for sure that it comes from these two boxes. So is there like some way in which you can make the sums very unique? Try to think like modulo some number. Okay, so suppose you put the cards into each box according to the remainder they give upon division by 3. So that's basically modulo 3. So if something is say 1 mod 3, that means its remainder is 1 when divided by 3 and so on. So let's just to clarify. So suppose you put everything that's 0 mod 3 here and 1 mod 3 here and 2 mod 3 here. So do you see what happens now? Any sum from these two will be 1 mod 3. Any sum from these two will be 3, which is 0 mod 3. And any sum from these two will be 2 mod 3. So based on the sums, you can identify the pairs. But is that the only way? So the thing is here we used mod arguments, but you can also use a size argument based on the size of the pairs. And this way is kind of hard to come up with anyway, so I'll just say it now. It's basically you take in one box, you just take one. The middle box, you take everything from 2 to n minus 1. Then the third box, you take n. So now what happens is if you take just these two, the maximum sum you can get is n. And the minimum sum you can get here is n plus 2. If you take these two, the only sum you can get is n plus 1. So you can see that like none of them can ever overlap because this one ends at n, this one starts from n plus 2, and this is n plus 2. So if you play around with this a little, you'll probably convince yourself that these are the only two ways. The thing is, you still have to prove it, right? So directly proving it just for some n or for 100 may not be very easy because there are like so many ways it could happen and you have to check each case, and that's probably not possible. but you can use induction. And in this thing, induction is really nice because suppose, okay, let's take the case in which n is not alone in its box, because this is a nice case where you can use induction. So the thing is, if n is not alone in its box, you can just remove n, and the thing is still valid for n minus 1 because none of the boxes are empty. So the thing is, if you remove n, then it should still work for n minus 1, right? And that is the motivation for using induction. So if let's prove that if you remove n, okay, first let's prove the base case. So base cases is like 3 and 4 because you need to have at least one card in each box. So technically you only need 3, which is like obvious that this is the only way. I would also prove it for 4 just to be a little safe because later you might need to use that. So even for 4, it's kind of easy because you just need to check a few cases. So I think you can do that yourselves and just try it as an exercise. So just assume you've proven the base cases 3 and 4, which are not at all hard. Now you need to prove that suppose you have n minus 1. In n minus 1, you know that these are the only two ways based on the inductive hypothesis. We assume it's true till n minus 1. And now you're adding n. So you're basically adding into either this configuration or this configuration. And you have to show that the only ways it works is the same configuration for n. So it might seem a little confusing, so we'll manually do it. So suppose we take the second case. You have 1 here, you have 2 to n minus 1 here, you have 2 to n minus 2 here, and you have n minus 1 here. This is the case for n minus 1. Now you're adding n. So you can either put it over here or here or here, right? So let's take the case in which you're putting it in this box. Now here the problem is you can take the pairs, say you can take you can take n and 2, and here you can take n minus 1 and 3. Both of the sums are n plus 2, but the sums should not overlap from different pairs, is what we know. So it's not possible. So suppose we're putting n over here. Then you can take n and 1 and then minus 1 and 2. So again, that's a problem. If you put n over here, then you can take this and this, right? So again, it's a problem. So you can't put n into this thing, right? So now let's take the other case. Everything from 1 modulo 3 is over here, 2 modulo 3 is here, and 3 modulo 3 is here. Now suppose say n minus 1 is over here. That means that according to our claim, n can only go here. So let's see what happens if you're putting n over here. Then you can take this pair and this pair, right? And you have a problem because both of them sum to n plus 2. If you put n over here, then you can take this pair and this pair. So it's again a problem. So you have to put n in this box. So you've proven in this case. And now you can just take a similar case when n minus 1 is over here. You can check cases like we just did. And you'll see that your claim is true. That only the way we showed over here can work. Now let's take the other case where n is alone in a box. This is just basically checking cases. So if n is over here and then you have these two boxes, I'll give you an outline of how to do it and then you can try it yourself. So first, suppose that 1 and 2 are in, you want to prove that 1 and 2 are in different boxes because that's how it's supposed to be. So suppose 1 and 2 are in the same box. Then if you have say n minus 1 over here, you can take these two pairs, right? So that means that n minus 1 should be along with 1 and 2. And now using similar arguments, you can prove that 3, 4, and everything would be in here, which would leave this box empty, which is bad. So you're done with, so 1 and 2 can't be together because then this thing would happen. So that means 1 and 2 must be separate. And now similarly, you can prove that n minus 1 needs to be here and then 3 and 4 and so on. You can try that yourself. It's not at all hard. So basically, you've checked both the cases. The really main thing was this case where we saw how easy it is to just take n out, reduce it to n minus 1, and induct, basically. So does anyone have any questions? Okay, I'm assuming there are no questions. If you have questions, please just speak and don't hesitate. So now we'll look at something called strong induction. So in the normal thing, we just reduced n by 1. We reduced the n case to the n minus 1 case. But here, we are just reducing. Like it shouldn't really matter if we are reducing it to n minus 1 or n minus 2 or something else. The point is we can reduce it, which means we can keep reducing it to the base case. So that's the main thing of strong induction, and it's like much more powerful than induction because all you have to do is reduce it. Like you don't have to think about what you're reducing it to. So let's try a problem with this. It's a kind of long problem, but it's actually a very nice problem. So this is basically, you can read the problem first and then I'll explain. Okay, so it seems like some complicated thing, but actually it's simple. It's just that there are some particles we call ions, it doesn't matter. And there is some relation which can be there between pairs of particles, which is called like entanglement. So when you have something like particles and relations between them, or something, and then there's like a pairwise relation between them, it's always very useful to think of graph theory. So if anyone's not familiar with like the basic definitions of graph theory, please say so and I can explain, it's fine. So you can think of these ions or particles as the vertices in a graph, and entanglement relation is basically the edge joining them. So essentially, you have a graph at the beginning, right? And they're saying that if a vertex is connected to an odd number of other vertices, then you can just destroy that one. So basically, if it has an odd degree, the degree is the number of edges going out from it. If the degree is odd, so for example, in this one, the degree is 3 because there are 3 edges going out. So you can just delete this. That's one thing you can do. And the second thing is, you can like make a copy of this, the entire graph you have. So suppose your graph is like this, then you can make a copy of it. And each thing in the original graph will be like also connected to its corresponding vertex in the new copy you're making. So it looks something like this. So basically 2 copies which are connected by the corresponding vertices. So those are the 2 things you can do. And you need to prove that just using these 2 operations, you can make just vertices which are not connected at all. So like a graph with no edges. You need to be able to do that using these 2 operations. So you can think about this for a while. Kind of like give hints in between, and if anyone has ideas, they can tell. Eventually, we can come to the solution. And you remember that you're trying to use strong induction in this. Okay, so since you want to use strong induction here, you basically want to reduce the problem, like with a certain number of vertices in the graph, to some graph which is less vertices. So, like, obviously, if there are some vertices with an odd degree, you can remove them and it's already reduced. So now what is the case that is left with you? The thing is, if you don't have any odd degree vertices, as in if all the vertices have even degree, that's what you have to work with. So everything is an even number of vertices going out from it. So like in that case, obviously you can't do the step one. So you have to do the second step, right? So just think a little bit about that. So let's see what happens when you have a graph with only even degree and then you double it. So suppose your graph is something like this. And notice that the degrees of all the vertices are even. So you have no choice but to double it. It's like an obvious first thing that you have to do. Okay. So your new graph looks something like this. And the nice thing that you have is like initially all the degrees in this thing, initially they were even. But now what has happened is each of them has a new edge going out of it as well. So all the degrees over here are now odd. And similarly, since this is like an exact copy, all the edges here are also odd because it's like symmetric. So that's a very nice characterization that you have. And now the thing is, you want to somehow reduce it such that, like you suppose you had initially n vertices, now you have 2n. You want to somehow reduce it to something less than n. Now you might be tempted to just again start like randomly deleting odd vertices, but the problem is you might just end up with something bigger than what you had before. If you just randomly do that, you can't guarantee you'll get to something smaller. So instead, you can try to do it in a structured way. So instead of randomly deleting odd vertices, what you can try to instead do is only delete odd vertices from one of these. So suppose you try deleting from, say, just this one. So let's take, say, this vertex and delete it. And then this one. Now all the things left are even degrees, so you can't delete it anymore. So even now you still have a nice thing because over here now you have everything even. But in this one you have everything odd. Right. So if you can work with this in some way, that would be nice. So one nice thing you notice is that the vertices in the red graph which still have counterparts in the old graph, let's just think about only those. So it's just these four in this case. So for these, if you think of these as pairs, Notice that like over here, it's all of them have, sorry, even degree. And here all of them have odd degree because it's not changed in each of these pairs. So now what you can do is, if you delete, say, this one, right, then its counterpart's degree, which was initially even, it's gonna change. It's gonna become odd because this green thing will go off. And now this one will be odd. That means you can delete this as well. So let's try doing that and see what happens. Okay, so now the thing is, initially, um, the vertices over here and the vertices over here, like on the red and on the black graph, whatever the degree was, it must have changed a bit because you right now you deleted two things. The thing is, however these yellow vertices degree changed, the same way the black vertices degree would change because you deleted this corresponding thing on both of them. So the remaining things would be affected in the same way. So that means initially this was even, right? Now it became odd. But now its pair, which was initially even, its pair, which was initially odd, it became even. Similarly, that happened for both of these as well. It may not happen for like all of them, but in this case, it happened to like switch for all of them. The point is that when you had those odd even pairs, and then you change both the graphs in the same way by removing the same things, if something's parity changes, its pairs parity will also change. Right? So again, you have odd even pairs. And similarly to how you removed an odd even pair just now, you can again remove one more. You can remove this and then remove this and so on. And you can keep going until you've removed everything from the black graph because everything in the black graph was involved in a pair, right? So as long as you can keep removing pairs, you can keep doing that. And now you just have some part of the red graph. Like some part of it has already been deleted. So right now you have less than n things, right? So basically you've reduced from n to something less than n. So you're kind of done, except there's a small extra case, which is suppose when you had your black graph and your red graph, and you started deleting everything that's odd from the black graph, suppose you just ended up deleting all of it. Then you're just left with the red graph, which is not really good. But that has an easy fix. It's just suppose you're about to like fully delete your black graph and there's just one vertex left. And you have your red graph here, which is something. Instead of deleting this, you can just delete this one instead because everything in the red graph is odd degree, right? So you can delete this one and then you split the whole thing into two smaller graphs. And this one would have size n minus one, like n minus one vertices. This one would just have one vertex. So in this case, you just reduced n to these two. So you're good. So in both the cases, what you've done is you've reduced n to something that's less. And that is what you wanted to do. And by strong induction, you're done. So I hope this example was clear to you. And if you have any questions about it, please do ask. So also problems you can try are IMO 2000 P1 and 2009 P6. Both of them are a little challenging, so you can do them if you're up for a challenge. And like if you want hints or you have questions about that later, you can ping me on the server. So now let's move on to Pigeonhole principle, which is called PHP. So let's start with a very simple example in this. So suppose you have 4 holes. You have say 5 pigeons. So suppose you want to put your pigeons in the holes, right? If I say that you must have 2 pigeons in one hole, that's kind of obvious, right? Because suppose not. Suppose you have only 1 pigeon in each hole. Then you have only 4 pigeons, which is a contradiction. You need 5. So there must be 2 in one hole. Right? This seems like a very trivial thing, but it does come in useful. So now suppose that you have 9 pigeons. So by the same argument, I know that there'll be at least one hole in which you have two of them. But can you say something strong? Can you say that there has to be some hole in which there are 3 pigeons? So suppose not, then each one would just have 2 maximum. Then you'd only have 8, right? But you need one more, so something must have 3. So can we generalize this is the question? So the thing is, suppose you have now n holes and k pigeons, so just say k things. You're trying to distribute the k things among the n holes. And so in a kind of informal way, if you look at it, you're trying to like minimize the largest thing that's there in some hole. And for that, you're kind of distributing evenly, right? So suppose you just try to divide the k things equally among the n holes. You take k by n. So suppose you have your 9 by 5 and you take your 9 by 5. And this is 2 and 1 by 5, right? Mhm. You have 4, right? Sorry. So you have 2 and 1 by 4. So basically you have more than 2, right? You need, on average, you need more than 2 per hole. So that means in some hole you have to have 3. So if you just take the ceiling function of this, which is like the smallest integer that's larger than this, you get 3. So the general statement of the strong version of pigeonhole principle is that if you have n holes and k things, then ceiling function of k by n, this number you'll have some hole with this number of things. Because otherwise, if you have, suppose like this is not an integer, okay? Then if you just have k by n or less in each hole, then if you multiply this by the number of holes, you get k by n, which is less than this integer. Suppose k by n is actually an integer, then it's a similar proof. Then you suppose you have maximum k by n minus 1. You multiply this by n, you'll obviously have a contradiction. So I hope the proof is clear that you need to have at least these many things in sample. Like it's very easy to just do a proof by contradiction. So problems with this are actually kind of fun in my opinion. So this is a nice problem, which is also kind of graph theoretic like the previous one we did. And you can think about this for a while. I think it's quite doable. So I'll give you like 4 or 5 minutes. I'll just rephrase the problem so it's a bit easier to think of. So this can be considered as a graph, right? Because people are like corresponding to each other. So the correspondences can be considered as edges in the graph, and the people are obviously vertices. So now the thing is that they're discussing 3 different topics. So it's 3 different types of connections. So you can think of that as different colors of edges in a graph. And what you want is you want 3 people who write to each other about the same topic. So you basically want like a triangle in which each edge is of the same color. So it's called a monochromatic triangle. So try to prove it in this way.
Okay, so I think we can do this like each vertex. So like let's say the vertices are P1, P2, so on till P17, and then each vertex has degree 16. And
Yeah,
so suppose we consider P1, then by PHP, uh, out of the 16 edges, six edges must be of the same color. At
exactly.
least six edges. Yeah.
Yeah.
So let's say those six edges are connected to without loss of generality P2, P3, P so on till P7.
Okay.
And say the colors are RGB
Okay.
and these edges are red. So now if from 2, 3, 4, 5, 6, 7, if there's any edge of red color, then you are done. You find a monochromatic triangle.
Yes.
If not, then you have the case basically you have six people and there are only green and blue edges.
Yeah.
So you have to find a monochromatic triangle with six people and only two colored edges. And
Yeah.
I think there exists a monochromatic triangle. That's a famous problem, right? With six
Yeah,
people.
it's Ramsey number.
Yeah.
Yeah, so we can prove that in a similar way. So now you just have six people. So let's say this guy is connected to five edges. Then by PHP, some three of them must be the same color. So let's say these three are the same color. Then if any one among these have red, then you're done. So suppose all three of them have some other color, but then that's a triangle. So you're done. Okay, great. So now let's look at infinite PHP, which is slightly different. Just says that if you have an infinite number of things and you have a finite number of holes, then some hole will have an infinite number of things. And that's kind of obvious because otherwise you would only have finite things and finite holes. So how are you supposed to get infinite things that way? Right. So I hope the statement is clear. And there's this problem which is a kind of fun problem. So you can try it for like 5, 6 minutes and see if you have ideas.
The wall is only on the outside, right? Like it cannot be like there's a square in the inside of the square, big square, and then there is a wall on the edges of that.
No, no, only on the outside.
Okay.
So what is like this?
This sort of seems like inductive. Like if you show for 9, okay, let's take like 3 cross 3 and draw 2 cross 2 square on the right, bottom right corner basically. And basically, like, you know that if for 2 cross 2 it's true, then wait, can you draw that once?
Okay, sure.
Yeah, and extend it to a 3 cross 3 now. Yeah.
Okay.
With red, can you wait? I'll use pen. I think I can. Oh, I cannot. Okay, can you mark with red the bottom right 2 cross 2 square, the boundary of that thing, the bottom right. No, not this. Right of this. Yeah.
Yeah.
So basically, like we know that in 2 cross 2 thing, eventually the ant gets a position where it's on the top right square of the red thing, and the
Okay.
arrow is towards the right, right?
Okay.
Only then it exits. And now in that case, suppose you achieve that situation, and then when the ant tries to move, it hits a wall. So it does not move,
Yeah.
but the arrow changes. So it goes up, right?
No, it goes down because of the arrows like this, then it'll go clockwise, so down.
Or it goes 90-degree clockwise. Okay, I was considering anti-clockwise. Hmm.
Okay.
Hello?
Yes.
Oh, yeah, I think I got it. We have to
Okay.
make sure if the insect cannot leave, then we have to make sure that the top right box is only entered at max 3 times.
Yeah, that
Yeah,
is true.
and and to show that, if I can show that any unbounded square must be left, I mean that an insect will always leave a square which is not bounded, then I can show that the boxes which are on the corner must be in some permutation will be entered infinite number of times.
Exactly. So, like by unbounded, you mean it's entered an infinite number of times, right?
Yeah,
Okay, so suppose this is entered an infinite number of times. What you're saying is these four will also be, right?
yeah,
Exactly. So if something is and if it never goes out, that means it stays inside forever. And something is entered an infinite number of times. It's basically infinite PHP. So if this one is entered an infinite number of times, you can extend it to these four as well. And then you can keep extending it because like the arrow in this will point in all four directions infinitely many times. Similarly, you can keep extending it and you must eventually get to this thing, which means at some point the arrow points this way. And so you're done. Okay, so now you can try this problem, which is a little harder, but it's a nice result. And I think it might be a kind of common result.
Wait, so like all the points are connected to all other points, or it's like not
Yeah,
necessary?
everything is connected to everything.
Oh, okay. So-
A hint which is kind of obvious is use infinite PHP. So just like randomly try it on some point and see what happens. Any ideas or do you want some more time?
I was thinking like if we can show even if there is one point which has like infinite one point which has the segments of only one color, then
Yeah.
obviously we'll have infinite because then just remove that point and the problem condition is still true, so the output will still be true. So just have to
Yes.
basically find one such point.
Yeah, but that's not really guaranteed, right?
Yeah.
So one thing is you can just take a point and you know that without loss of generality, it has infinite, say, blue edges, right?
Yeah.
So try to continue that argument and see what happens when you're not able to continue that. Okay, so I'll give a hint. So suppose you have a point and there are, say, infinite number of, say, blue edges coming from it. And these are all the vertices which are connected to it through a blue edge. And this set is also infinite. Now, in this set, suppose you can find a point which also has infinite blue edges. and that goes to like some infinite set of vertices. And again, if you can find a point and keep going like that forever, these points which you're finding, these can make up your infinite graph of only blue edges. Now the problem happens when you can't find such a point. So that means that in some infinite set, none of the points is connected with an infinite number of blue edges to others. What does that mean?
So like one point must have infinite right edges.
Not just one point, all the points. Because if
Okay.
you had any point, then you can just take that.
Yeah.
Like, aren't you kind of done? Because you just want infinite points with some particular color. So if you have infinite points with red edges, okay, so what you can do is now you can start using red edges instead of blue, right? So you take some vertex here, you know it's connected to infinite things with red edges. And you repeat that argument. And now you can't run into a problem because then it would be like each point is connected with finite things with blue edges and red edges. That's obviously not possible, right?
Yeah.
Yeah. So if it doesn't work for one color, you just start it with the other color and that has to work. I hope it's
Oh, I
clear.
think I misinterpreted the problem then. I thought the problem meant that there are infinite number of points. So like in the original graph that they're only connected to, so like there's some point which is connected to all the points at the edge of one color. I did not I don't think
Oh,
that you
okay,
meant
okay.
subgraph. Yeah, that's why I was confused. Okay, this
Okay.
makes much more sense. Yeah.
Yeah. Okay. So we'll do some more PHP problems. I didn't write the problem statement. So this is a nice problem. It's like you have an equilateral triangle. You have 5 points inside it, some 5 points. You have to prove that there are 2 points, and so the side is of length 1. You have to prove that there are 2 points whose distance is less than or equal to half.
Oh, I think I'm done. But I think
Okay,
I've seen the idea before. So I'll
okay.
probably not. Yeah.
I'll wait for somebody. Okay, so the main idea here is you divide the triangle into four smaller triangles because you have five things here. If you want to use PHP on them, you want like if you want two of them in the same thing, then you kind of want four things. That's the motivation. So a nice way to divide this into four parts would be by taking the midpoints and joining them. So you have four smaller triangles which are congruent. So now by PHP, two of the 5 points need to be in the same triangle. Let's just suppose it's over here. And it's kind of obvious that if 2 points are in the same triangle and this one has side lengths half, because the original one had side lengths of 1. So if 2 points are in the same triangle, then the distance between them must obviously be less than half. Right, so that's that problem.
Also, once you see
Yeah.
that you want to divide it into four regions, and like you see that you want to prove d is less than equals to half, so midpoint is sort of motivated because half is like half of one, and one is the side length. And then you see, okay, when you draw midpoints, there are clearly four divisions, so that you can motivate the divisions as well.
Yeah. Okay. I'll give one last problem, which is kind of simple. So hopefully you can do it fast and then we can wind up with the class. So it's a kind of common idea that you have like five points with integer coordinates. And you want to prove that the midpoints of the five of the line segments you can make with the 5 points, some midpoint has integer coordinates. This is what you need to prove.
Hello.
Yes.
Yes, I think we can do this with the parity one. Let's say 1 point has a parity of 1 and 0. Then
Okay.
at max we can make 3 more points such that they have their parity does not match.
Yeah, you can make these three.
So if we introduce any other point, then one of these parities must match.
Exactly. So it's like you have four possible parities, but you have 5 points. So some 2 points must have the same parities, like what you said. So whatever the parities are, like suppose it's without loss of generality 1 and 0, then if you add them and then you divide by 2, which is how you find the midpoint. So it'll be 1 plus 1 by 2, 0 plus 0 by 2. Like something plus the same thing by 2 will give you something like which is an integer, right? Because this is even and this is even. So you're done with that problem. And yeah, I finished the class now. So I hope everything was clear. If you have any doubts, then you can ask right now. Okay, so assuming no doubts, you can end now. You can stop recording.
Okay. Thank you for the class.